This week, I will continue with the next chapter, which is chapter 4, which is control signal transmission. So, can you see this the screen here?
Nampak, Doktor.
All right, good. Thank you very much. All right, for control transmission signal, okay, we have learned about the sensors, we have learned about the control valve, and we have learned about the overview or introduction about the instrumentation and process control. Now, we come to a section in which how we transmit the signal from one element to another element. Okay, for example, we have the sensor. Sensor could actually measure in terms of temperature, in terms of pressure, etc. And then how this going to be transferred, the data is going to transfer to other element so that it's become useful. Okay, for example, temperatures, how to convert the temperatures into the voltage so that this one can be digitalized, or this one can be transformed into the in terms of the useful data in the control room. Okay, of course, if the temperature, the data of the temperature cannot be transmitted as it is, as the temperature, it need to be somehow to be converted into other signal forms, so that it's become readable, readables to other element. Okay. Wait, and then this one. Okay. In this chapter 4, we're going to look at the some transmission issues, analog signal transmissions, and then digital transmission signals, and then last for this chapter is about the transmission technologies. Okay, we will look them all into details in the next few slides. Okay, transmission signal. Okay, if we look here carefully, we can actually see this is, we have two main domain, the regions. One is sensor part. Okay, one element, for example, this one is the sensor, and the other part is the control room. All right. Okay, how are we going to transfer the data from the sensor to the control room? How are we going to transmit this data? How are we going to transmit the data in terms of the valve, the measured pressure, to the control room? Okay, if you can see here from this sensor, temperature sensor, the parameter, the variable parameter is actually the temperatures. Okay, the temperature. And if you look at the valve point, and of course the variable parameter will be a pressure, for example, or flow, and so on. Okay, these two input parameter, either temperature, either flow, either pressure, etc., need to be transmitted to the control room. So how this data or signal to be transmitted? This temperature need to be converted into some sort of maybe we going to convert into in term of current, maybe in term of voltage. It depends to what we want, to what the input, required input in the control room. Okay, as well as for the valve, we're going to transform the input parameter in terms of pressure, PSI, 3 to 15 PSI, into the voltage. And then how we going to communicate to the valve? Again, we need to transform the voltage into the PSI. So this is what we call as the transmitted signal from the sensors and to the control room, or any kind of the device. In this case, instrumentation and process control, we are particularly looking at the sensor to the control room, so that the control room, the brain of our control system, can analyze the requirement, the requirement of current condition, whether, for example, the valve need to be opened, need to be closed, or need to be shut off, need to be reduce or increase the pressure, etc. So they have to communicate. They have to communicate. This is a very simple example that you can see the importance of the transmission, signal transmission. Without this one, without the transmission signal, the sensor definitely cannot be controlled by a control room. The sensors cannot transfer the data to the control rooms, and we cannot, we need to rely on the inside gauge. So there is a very important element in the instrumentation and process control. Equally important, I would say equally important, which is as the other elements. Sensor, without sensor, we cannot measure what's happening, what's going on for the sensor, for the temperature. And without the signal transmission, the sensor seems no use. It's not like variables, because the data cannot be transmitted to the control room, and vice versa. Okay. So that is signal transmission, and now we come to the signal conditioning. Okay, what is the difference between signal transmission and signal conditioning? Okay, signal conditioning. Okay, signal conditioning is related to how we going to convert. Okay, wait. How we going to convert the temperature into a voltage or current? How we going to decide on this matter? That is what we describe as the signal conditioning, in which we're going to provide the conditions for the signal, a suitable condition for the signal to be measured, to be accepted by the control room. I mean, to be readable between two elements. Okay. You can see here, transmission associated with the signal interface between some element in the process control. Some elements means that not necessarily to be with the control room. It could be a sensor with the control room. It could be a sensor with the actuator. Any kind of combination of the elements in the process control. Okay. This is what we call as signal conditioning. Okay. Signal conditioning refer to operations. Operation performed on signals to convert to a form suitable for interfacing between one element and another within the control room. Within the process control loop. For example, as I mentioned, the pressure or actuator or valve need to communicate to the sensor. Sensor need to communicate to the control room. We need to provide a very suitable condition so that the signal from the data, from the sensor, from the actuator can be read, can be digest by each of the required element in the process control. So if we look at these figures, okay, we have here the process, okay, and we have the sensor. Of course, the process we will have the maximum and minimum values, like a water level. There are cases in which the water level will come to the very minimum level, and it fluctuates to the maximum, etc. And this data need to be sent out to the sensor. The sensor measure the difference in terms of this range, and then the sensor will transform this data in terms of Y, whether it's maximum or minimum, and this is where we use the signal conditioning to decide to transform from one signal, the type of the signal into another. Okay. Okay, some transmission issues. Okay, transmission in this signal. Okay, so we need to know, we need to decide, or we need to solve between the range. Okay, if we are boiling water, a pure water, we know that water, probably the temperature is within 0 to 100. That is what we call it as pure water. If we have tried to boil an oil, for example, the range might be different. Maybe it's from 100 to 500 degrees Celsius, etc. It depends to the parameter that involve within the specific case in the process control. And then we come to the accuracy. If you have the wide range, we may need to compromise with the accuracy. Okay, and the sensitivity level might be different. Okay, linearity. Okay, the change in the input might cause a change in the output. Okay, so we need to have a very precise linearity. We need to decide for the linearity so that the changes in the output, in the input will cause a change in the output linearly. Linearly. Alhamdulillah. And the noise. This is the disturbance from the outside, the signal, and we are looking in terms of the signal. And the disturbance from the outside that might cause a distortion to the values or reading displayed in the control room, especially in the during the measurements. All right. Okay. Analog signal transmission. Okay, what is analog? Okay, analog signal transmission. Analog is very simple. Is the analog. I mean, it's analog signal, straightforward. The measurement is with the gauge and everything. So it's not digitalized. If the pressure is 7, it will read the 7. Alhamdulillah. And then it is a straightforward values. Okay, so we need to know for the analog signal conditioning, we need to know signal level. Okay, we need to know the bias change, the bias, the difference. We need to know the linearizations, and conversion, because sometimes we need to convert the temperature into the current temperature in terms of voltage, because we want to know what is the other element on the other side. Okay, so that's why we need to convert. Sometimes we need it required for filtering, and sometimes it will be amplified. These are some of the most common signal conditioning. See, signal conditioning in instrumentation and process control. Level, bias, change, linear, conversion, filter, and amplifier. Okay, in this section, in the next section, we will going to review all of this, each of this genre type with the circuit. Okay, how you going to achieve the linearizations? We're going to have some electronic circuit. How we going to have a conversion? We need to have a conversion circuit. Filter, we need to have a filter circuit. And amplifier, we need to have the op-amp circuit. Okay, so that the data become readable and useful for analysis and evaluations. Okay, analog signal. Okay, for the first one, signal level and bias change. Okay, sorry for this one, should be, the title should be slightly different to the text, but it just turned up to be the same. And I just use whatever been prepared by Dr. Wahyu. As you can see here, it's prepared by Dr. Wahyu. Okay, so a method to adjust the level, magnitude, or bias zero value of voltage signal. Okay, sometimes what happened? Okay, sometimes what happened, the value of the incoming or the input values may not fall exactly on 0, may not start exactly on 0. In this case, 0.01, and maybe 0.1, and maybe 5 volt. Okay, the value not start from 1. Okay, what will happen? We need a signal conditioning circuit. We need signal modifier circuit to amend this value to make sure we calibrate. So the output values, the values goes to output will be 0. so that it start to zero. It start with zero. Regardless, no matter what, whether the value start here is not zero, so we need to do something so that the signal here become zero. That is one for measurement purpose. And sometimes what happen, the measured value is, okay, first we have this one 0.01 to 0.06. And the output here is in terms of volt. If this value is to be used, for example, 0.01 at the input of the other element here, maybe this one is not readable by this one. So like it or not, we need to do something, modify the signal so that it's become readable to this parameter in control room. Probably the input for this one, the range input maybe 0 to 10. So since the input at the sensor side is very, very low, 0.01 volt, so we need to do something, which is we need to amplify. First, okay, so what we have to do for this circuit is actually first we need to include two circuits, okay? First, we need to make sure these values will come to zero because it not start with zero, it start with 0.01. So we need to make these values to start at zero by using a bias circuit, okay, or zero shifting circuit. Now it's become zero range to 0.05. That's good enough. But however, why it's not readable or useful in this case is because the input parameter at this section, at this element, is unable to read this value because this is too low. It's less than 1 volt. So what we have to do, we need to include another circuit, amplifying circuit, so that we can actually magnify or increase or amplify these values to some other value that is readable to this section, right? So for this case, for this example, we have the input 0.01 and the output for this one, or input for the control room, is 0 to 5. So we need to do first is zero shifting. We need to shift the zero, and then the second one to amplify. Okay, can I ask you whether we can amplify first, then we go for zero shifting? Anyone? Anyone want to try? Can we, Sabrina?
Yes, Doctor.
Okay, Sabrina, what do you think? If I'm going to amplify this value first, then I'll do the zero shifting circuit. Means that the circuit, swap between these two. Can I do that? Can we do that or not?
I think can.
Why?
I think zero shifting untuk kurangkan dia punya noise kan?
Not really. It is to calibrate the value so that it's come to zero. Okay. So the answer is yes, macam awak cakap, but your justification is not really accurate. So actually you can amplify first. Okay, you've got a very low signal, and then what you need to do, you can amplify first, then you go for zero shifting for the second phase. And you can zero shifting first, then you can amplify the signal later, no problem. So in this case, it's just a matter we need to construct the circuit, whether the suitability, what need to come first. It depends to the application. Okay. So next. Okay. Next, this is bias. This is signal level and bias. So we want the level to start at 0. We don't want to start at 2, at 5. So you need to calibrate so that it start with 0. Sama juga. It's just like you got a weighing machine, a scale or weighing machine. You want to weight yourself, you stand up. But if your mission, I mean, if the scale is not start with 0, what you will do, you will shift the calibrator so that it start with 0, right? That is how you that is how you want to see the signal. I mean, to see the readings, so that you can see, oh, that is my weight. You don't want to go for like okay, the needle start at 5 kilo, and then you go on the scale, and then it show 45 kilos, and then you have to minus later, or 45 minus 5, or it's become 40. Oh, my weight is 40. That is a long way. So it's better for us to make it to start at 0, and then you simply stand on the scale, and then you can straightforward see, oh, it's 40 kilo. Okay, that is the intention. Okay. And for the second, this one, okay, signal level and bias. Now we come to the linearization. Okay. Linearization, this one is related to the linearity. Okay, linearity referring to our max. Y equal to mx plus c, kan? The linear graph. Okay, y equal to mx plus c. But in this case, since we are dealing with the voltage and current, so V out, y, which is y, V out is equal m. M is equal to the slope of the graph, and V is equal to the V in, and plus C is the cross section at the y-axis. Means that what value we start? We start at 5 volt, we start at 0, we start at 10, we start at kV. These are the very fundamental what you call it, equations for linear plot. If you can see here, okay, we've got the values here. Okay, theoretical line, we've got this one. Okay, we have the non-linearity errors, in which, okay, the signal might not perfectly linear, a straight line. It might have some errors, and this is the function. So it's depend to what value that we're going to use. This is the need for instrumentation engineers or control engineers to decide what the best function to be used for each particular application. Okay, now we have this one. Take a note at this very simple linear equations. And then we have a divider circuit. Why we need to have a divider? As we aware, the divider circuit is actually to convert the very high voltage, for example, high voltage or high current, to a relatively low values. That's why we need to have R1 and R2, and then we have the divider. So that this is the divider equations, in which V, okay, V at this point, V divider is equal to R2 times Vs. Okay, Vs is supply voltage, divided by R1 plus R2. This is the values that we're going to measure here. Okay, this is a divider circuit. I think you have learned this in the electric circuit, back in semester 1 or 2. Okay, let's have a look at this simple work example. Okay. So we have the divider of figure 4. Okay, assume the previous figure has value resistance of 10 kilo ohms, and the voltage, supply voltage is 5 volt. Okay. Suppose a sensor is suppose R2 is a sensor whose resistance varies from, have a look here, 4 to 12 kilo ohms. because this is the portable or variable resistor over a range. Then finds the minimum and maximum of VD, voltage divider. B, the range of output impedance. And C, the range of dissipated power by R2. Okay, what is R2? Well, R2 in this case is actually a sensor. Okay, it's actually a sensor. Okay, we have R1, R2. We have VD here. So what is R2? R2 is actually variable resistor. Why is variable? Because, okay, simple analogy, assume this is the temperature sensor. Okay, the temperature sensor. Okay, we put the temperature sensor to the any process, and then a moment that one got heated, the value of the resistance of this variable resistor will of this sensor will change. Maybe at 0 or maybe at 50 degrees Celsius, this will give a certain reading, say 10 kilo ohm. Okay, at 100 degrees Celsius, this one will give us, for example, 20 kilo ohms. So that's why this value varies depend on the thermal heating. And then when it varies, this one will give a different values to the VD. Because this one is variable resistor ataupun variable resistor within a sensor. So next, how are we going to calculate? First, the minimum and maximum VD. Okay. How are we going to calculate the maximum and minimum VD? Okay. We have this value. Take a look at this formulations. It is a very simple maths, but if you unable to use it, very difficult for you to answer it in the work example. Okay, what is the question asks what is the minimum and maximum VD? So we know the formulation of VD is equal R2 Vs divided by R1 plus R2. So we know all the values here, Vs, R1, and we know the R2. Okay, we know the R2 is 4, the minimum is 4 kilo ohms and the maximum is 12. So what we need to do is actually first we use the R2 equal to 4 to replicate the minimums, and then we consider the second case R2 to be 12 so that we can calculate the maximum and minimum value of VD. Okay, settle. So, first question. What is the range of output impedance? Okay, how we going how we calculate the output impedance of resistor? Okay, this is again the electric circuit that you've learned in the first or second year. So the impedance of a current is actually the impedance of the output impedance of the resistor is actually the calculations of the impedance in the parallel conditions. Okay, in the parallel condition. So we know the range. When the questions ask the range, so we know it's a maximum and minimum. So, and if you can see here, as I explained to you before, VD minimum. So we use 4 because it says 4, R2 equal to 4. And for the R equal to maximum, 12 kilo ohms. And then it'll give us 2.73 volt. Okay, so the range of the voltage divider is actually from 1.43 up to 2.73. I want to ask you, okay, Fikri, Nabil Fikri. Nabil Fikri ada tak? Are you there? Okay, Nabil, I want to ask you whether these values 1.43 and 2.73, do you think it can go up to 3 volt for this one, the maximum? 273, can this sensor goes to 3 volt at the voltage divider values?
Can.
Boleh? Okay, boleh. Sebab apa? Why? Why do you think this can go up to 3? Huh? For R equal to 2, this can go to, how are we going to obtain D? I mean to get 3. How? Ada yang nak tolong? Adi Shisha.
Yes, doctor.
Do you think this values 2.73 can reach 3.0?
Can, doctor.
Can. Why? And why and how?
It depends on the resistance.
Okay. Depend on resistance. That's right. Okay. But here, it clearly mentioned that R2 is a sensor, right? It's a sensor whose resistance varies from 4 to 12. It's clearly mentioned that it's a sensor and the sensor have the resistance maximum 12. So how can we reach 3 here?
Even that way, I think it's not possible to reach 3.
That's right. That is not possible, okay? I want you all to understand what is mentioned by range. So the maximum will be 2.73. That is the maximum. Why? It's because it's clearly mentioned that R2 is a sensor, and the sensor has the resistance maximum is 12. So it cannot go, definitely you cannot reach 3.0. Why? Because the maximum of the R2 is actually 12. Right. So, and the same goes to this one. Can we have this one 1.0? The answer is no, because the minimum resistance is 4. All right. So you have the limit between 2 points, because this is the sensor. Once you have the resistance within the sensor, that's it. You cannot change unless you change the resistor. That having the capacity, for example, it start from 1 kilo ohms up to 20 kilo ohms. Then this range might be different, right? Do you agree with me, Adi Shesha?
Yes, doctor.
Yeah, I hope that make yourself or everyone clear about the range. The range is tolerance between 2 points, maximum and minimum. Can we go below than minimum? Can we go below the maximum? No, unless you change the device, unless you change the sensor. Okay? Can we go beyond the maximum? Otherwise, we wouldn't say that as a maximum. That's why you cannot go beyond the maximum level. Okay? If you ask me, you calculate the value and then we've got the value 2 here. And I ask you, if this value 2.0 can be lower or greater than that values, the answer is yes, as long as it is within the range of this one. Okay. So for the second question, the range output impedance. Okay, the range of output impedance. Have a look at this one. Okay, as I mentioned before, the impedance of the values can be calculated by consider the two sensor as a parallel. Okay, now I want you to calculate these values. Okay, grab a pen or calculator or anything. I want you to show your calculations. Okay, very simple one. the output impedance. So you know the R1 in parallel with R2. R2 you know is 4 is the minimum, 12 is the maximum. So I want to see whether you able to obtain this value. I'll give you 2 minutes for this one. How to obtain this? Simply consider these two resistor as what? As a parallel circuit, as a parallel. That is what we call as impedance. Because it's 1/. I will pick randomly from here, and you need to switch on camera and show your calculations. 2 minutes, I'll give you, okay? Try to perform your simple calculation and show to me right on your camera and then your calculations. Kau tak tidur ni petang-petang ni. Okay. Siapa yang dah dapat? I know. Who want to volunteer? Volunteer mudah. Saya dah tak tanya nanti random nanti. You dah boleh bertenang. Anyone volunteer to show your simple calculations how to obtain the output impedance for the maximum and minimums? Anyone? Volunteer. This one. Cepat. Whether you've got this one or not. 286,545. Boleh? Volunteer? Two resistor in parallel. How? How you calculate two resistor in parallel to get the output impedance? Okay, Hakimi lah.
Yes, doktor. Tak dapat lagi, doktor.
Apa yang tak nampak?
Tak dapat lagi parallel.
Tunjuk kamera. Saya nak tengok kat mana yang awak tak nampak. You calculate dekat mana you stuck. Kimi.
Jap.
Tunjuk. Apa yang stuck kat mana? Cepat Kimi. You on camera and then show your calculation. I want to see at which point you stuck.
R1 dengan R2 kena parallel doktor?
Saya dah cakap tadi kan. Takkan bila saya panggil baru nak tanya soalan. I ask you to ask questions. Apa yang tak faham, anything. Mana Kimi? Tunjuk. Saya nak tengok you tunjuk dulu.
Nampak tak doktor? Belum doktor, saya baru tulis. Saya tak buat calculation lagi. Nampak tak?
Tak nampak. Ada volunteer nak bantu Hakimi? As I said, volunteer kalau dah volunteer, dia bab-bab random, nak tanya random, okey lah, boleh. Ni sikit.
Saya dapat doktor.
Mana? Apa, Haris
Doktor.
Tunjuk Haris.
Kejap.
Dalam kamera tunjuk je paper awak tu. Dekat sikit Haris, dah nampak? Okay. Alamak. Kalau tak share tak nampak kan? Okay. Okay,
Nampak
thank you.
tak?
So, nampak. Tak tahulah kawan yang lain tengok ke tak. So, thank you Haris, Akmal.
Okay,
So, you calculate just by consider the two resistance to be parallel, right? So, apa yang kita buat for minimum 10 times 4 over 10 plus 4. Betul, Haris?
Betul tak?
Okay, so you do that one for the minimum is you consider R2 equal to 4 and for the maximum R2 equal to 12. That's it. You will get 2.86 plus 2.54. Try yourself. Don't take for granted, please. If you take for granted, the same things will happen just like your test. Nampak simple. It looks simple, very simple. But when you try to calculate, ni macam mana? Okay. Alright, the last one is the range of, when it says the range is very simple. We just stick to minimum and maximum. That is what we classify as range. How to calculate the dissipated power? Okay, dissipated power can be calculated by VR over R2. Okay, VR over R2. What is VR? So we know the VR. So we know the R1, R2. So we can simply calculate this value and that will give you 0.51 milliwatt up to 0.62 milliwatt. Okay, this is the thing. This is the one that normally for a sensor, for anything, for electronic equipments, you will see there will be heat loss in terms of joule heating, and then your computer start to heat up, your battery start to heat up, your adapter start to, the temperature of the adapter start to rise up, is because of this one, because the heat dissipation. So the range for the maximum and minimum will be 4 up to 12. So you plug in this value, that will give you straightforward the answer. Okay, this is just divider circuit. Okay, divider circuit. When we're going to use this, we may need to use this in combination of other circuit. Okay. Now we come to the analog signal for the conversion. Okay, have a look at this one. We have the conversion circuit. Okay, and we have the formula. You don't need to worry about the formulation, how they derive this one. You don't need to worry. It just matter, we know the existing of the voltage to current circuit. Okay, we have the amplifier, we have the, voltage drop across the R load, everything. They design the circuit already for you. So we know this one, the input of voltage will be, the output will be the current, because we're going to transform one signal in terms of voltage into the other signal in terms of current. So these are the values that we need to know. RML is actually maximum load resistance. V saturations is the op-amp saturation voltage. IM is actually the maximum current. So we have this circuit. So instrumentation engineer, control engineers, yes, this one is already on market. What we need to choose is actually to decide for the value, what is R1, what is R2, what is R5. These are the value that you need to determine in order to obtain the voltage to current. Depends on the range that we need. Some might need range in terms of 0 to 5, 0 to 10, 0 to 100. So you need to decide for the values, and the current values. Some we may need 0.1, 1 milliamp up to 10, 10 milliamp up to 100 milliamp, for example. Okay, these are the things we need to know and to design based on each particular applications. Okay, now we have a current to voltage. Okay, before we have voltage to current, and now we have the current to voltage. How? These are the circuit that we can use to convert the current signal into the voltage signal. Okay, these are the circuit. If you want to convert the voltage into current, this is the voltage into current. So we need to use this circuit. If you want to use the current to voltage, we need to use this circuit. Okay, so it's already there. So, and the formula is V out is equal to IR. Okay, so we know the I values, we know the R, so we will have the V out here as the output values. Okay, the same goes to the same goes to other RC low pass filter. Okay, we have the low pass filter circuit. What we need to know, or what we need to calculate is actually the R and the capacitance, and these are the formula. V in, V out over V in equal to 1 over 1 plus fundamental frequency divided by frequencies to the power of 2 time square root. Okay, so these are the formula, the values that we need to calculate. Okay, this is low pass filter, this is high pass filter with a certain formulations, and we need to design what frequency domain we want. So we need to decide based on this circuit. Okay, doctor, can we change the circuit? Can we change the circuit? Okay, the one that I shared with you here in the slide is the most common or the most proven circuit. Okay. Yes, you can establish yourself as long as you got the values. Okay, as long as you've got what you need, as long as it able to serve you as a low pass filter, high pass filter, the voltage and current, you can do anything. Okay, it's not limited to this one, but this is the most proven or the most well-known circuit for voltage to current, current to voltage, low pass filter circuit, high pass filter. This is the most common and constantly used in practice. Okay, but if you are genius enough, you can establish by yourself, no problems. Okay, now we come to another problem, issues related to analog signal transmission, which is amplify the circuit. Okay, we have voltage follower, we have inverting amplifier and non-inverting amplifier. Okay, this is voltage follower. Why we call it voltage follower? Because V in V out will follow whatever V in. Okay, so if we plug in here 5 volt, the value of output will also remain as 5 volt. That's why it says voltage follow. It just follow whatever being supplied at the input side. Okay, I want to ask CK, what do you think the need of this one, CK?
Yes,
If the values of input is identical to the output, what's the need of this circuit? No point, right? Macam the value 5 and then output is also 5. What's the need of this one? It's not amplify, it do nothing. So what is the purpose of this one? What do you think?
What I think.
What you think? Kan, kalau logik akalnya, you can actually just feed in directly the V into this one. You don't need this circuit.
Yeah.
Right?
Understand.
But why we need the voltage follower? While the value input and output is just the same. If you eliminate this one, you will get the same to other elements. Then why we need to use this one?
For protection of what?
Okay, good. Good. It's for protection. Okay. Some element we call it isolation purpose. Okay. Some element you don't want to be raised on the other side. What you need to do, you need to introduce some sort of circuit as a isolation. If anything happen on the left side, it won't affect on the right side. That is the reason of to establish this voltage follower circuit. Good. Okay, differential amplifier. This is the circuit. Okay, this is the circuit we can just use V1, V2, and we have the output. And this is the formula of the circuit. So this is the basic differential amplifiers configurations. And then we have V1 and V2, and we have one V out. So it depends to application. And for this one, can you propose a circuit to achieve input isolation for instrumentation amplifier? Okay, so by consider this one, can you propose a circuit to achieve input isolations for instrumentation amplifier? Okay, by looking at this one, we know, like CK mentioned before, isolation for safety purpose. So in this case, we know we may need the isolation circuit, and the second one we need the amplifier circuit. So there are two circuits that we need to use. So what we can do is actually we introduce the isolation circuits, this one, and the amplifier circuit. So combine these two, that will give us a certain configuration that will serve as isolations and amplify the signal that we have. All right. So an instrumentation amplifier includes voltage follower for the input isolations. Okay, this is the inverting amplifier. Okay, inverting amplifier. Sometimes you want the inverting V out, you want to be minus. So these are the circuit and these are the formula. So we just what we have to do is actually mix and match. Okay, you know your objective is to provide isolations, to amplify the circuit, to what else? To perform a low pass filter. So you need to add 3 circuit: voltage follower, amplifier, and low pass filter. So you need to combine all of these circuit to be a big main circuit, so that it can serve the objective of this one, in which the input need to be transmitted to the output. Okay, non-inverting circuit, these are the formula. Okay, I don't want to go in great detail. I just introduce to you the basic and the fundamental circuit as well as the equations. Okay. Okay, this is how. Okay, look here, analog signal transmission. Okay, we've learned several combination circuit, several type of circuit, and now this is example of circuit how signal condition can be achieved for a desired objective. Macam saya kata tadi, combination of 3 electronic circuit to obtain the objective. Have a look here. Okay, what we have here: amplifier circuit, we have voltage follower, we have divider. So you combine all of this circuit, will give you the required voltage output. It depends to your application. We need to combine all of them. I mean, to combine 2 or 3 circuit to achieve one objective. Sometimes you may need only to have 1 circuit. Sometimes 2, sometimes 3, sometimes 5 or more. Okay, depend on the applications. How to achieve this? This is what engineer has to do. Okay, this is the thing that instrumentation engineers have to deal with. Okay, you know your application. You want to measure, your vessel will measure this one the temperature will be between 20 to 50. And then you need to know the sensor, what best sensor to suit this one. And then how this one is going, that the data from the sensor is going to be transmitted to the control room. Okay, and these are the things that you need to design. And sometimes, and most of the time, these circuit are readily available in market. They already make it one piece for you. If you dice in the block, you should be able to see electronic circuit within the box, which perform this kind of things. All right, and then what's next? Then inverting. Okay, this is example. Okay, let's check this one. Simple example. A temperature is to be measured. Okay, a temperature is to be measured in range of 0 to 250. Okay, you know, you have a vessel, you are the engineer, you want to measure a sensor range. You know the oil, that the oil will have a maximum of the boiling temperature of 250. So you decide is between 0 to 250. The sensor is a resistant, as we discussed before, varies linearly. Have a look at this keyword, varies linearly, from 60 ohms to 350 ohms. So what happened? So you know, okay, so we know from here, we know that, okay, at 60 ohms, the value will give us 0 degrees Celsius. At 350 ohms, the value will give us 250 Celsius. Okay, for this temperature range. Okay, power dissipated in the sensor must be kept below 6 milliwatt. Okay, determine the transfer function. Okay, determine the transfer function. Okay, we review previously some transfer function. These are what we call equations, or another word for this one is a transfer function. Okay, these are the transfer function. These are the transfer function. These are the transfer function. Okay, so determine the transfer function equation of the signal conditioning that provide a voltage varying linearly from 1 to 5 volt for this temperature range. And then determine the current flow in the sensor at the maximum temperature. So have a look at this keyword, maximum temperature. So maximum temperature is 250. At 250, the value of the resistance is actually 350. So we try to figure out what the question want from us. Okay, so that the maximum power dissipated in the sensor is less than 6 milliwatt. So we've got the values. So here, the first thing that we need to do, okay, as I mentioned to you, it says here varies linearly. So we know what we need to do is actually we need to go for linearization, which is V equal to amps V int plus V naught, Y equal to mx plus C. So we need to use this formula. Okay, how? Okay, first we establish, okay, Y between 0 and 60, and the second equation is 250 and 350. We try to relate this one to obtain one formula. So we have V out M Rs plus V naught. Okay, so we have V out here is actually, okay, we know the V out is actually, for the first question, V out is actually 1 to 5 volt. So the V out is 1 and the other V out is actually 5. So V out is 1, 60 is what? 60 is the resistance. And the V naught is actually 0. So we have another equations, 5. We have the resistance is 350. And M is the slope. So based on these equations, okay, we can actually calculate what is M. Okay, you subtract or you solve these quadratic equations, these two equations to obtain the M's. You can simply use calculators if we want, or you can manual calculation. Equation 1 minus 2, that will give you M as 0.014. So we know the value of M is 0.14. So by using the first equations, look here, 1 equal to 60 times M, when it's really 0.0148, so plus V naught. Okay, then we plug in the values, then we should be able to calculate the V naught, 0.172. So the transfer function for this equation will be V out equal 0.m M, this M, 0.148 times RS plus V0. V0 is 0.127. So this is your transfer function for these conditions. This is the one. Okay. The second question, determine the current flow, the maximum temperature. Okay. So we obtain the value. Okay. The current flow P, power, equal to I squared R. Okay. So we know what is, so we know the power which is 6 milliwatt. We don't want the values to go exceeding 6 milliwatt. So 6 milliwatt equal to I squared times 350 because it's maximum. So we will have current as 4.14 milliamps. So the maximum current flow, okay, the maximum current flow is 4.14. Why we call it maximum? Because the sensor can only measure up to 250 volt, can only measure up to 350 ohms. That's why the maximum current flow within this one is 4.14. Consider the maximum values, which is 350. Okay, so I hope this one very clear for you to understand how it's operate. Okay. Any questions so far? Hakim, do you understand this? Hakim? Sabrina,
Instructor.
faham tak? Do you understand?
So far faham.
Farid? Ahmad Farid? Ahmad Farid? Amir Amirul?
Faham doktor?
Faham
Faham.
Okay, kalau if you have any questions so far at this point, please let me know. And even if you want me to explain again, yes, I'll do that. If not, if you still blur on certain part, have a look and try to do some your own homework, and then you should be able to address this. Okay. Now, okay, we've done on the analog part. Okay, we have done about how to linearization, how to amplify the circuit, how to to process the signal so that it's become readable. Okay, so now we come to the digital signal transmission. Previously is what? Analog. Now we have a digital. Why digital? Because nowadays everything is digital. Okay, as simple as that. Okay, all the control room elements are digital. We need to convert the analog signal into of digital. What is digital? 101010 combinations of digital binary numbers. Okay. So we have analog sensor, we have op-amp, operation amplifier, and then now we have ADC. ADC is analog digital converter. So the analog signal will be converted into digital, and the final data will be in term of 1111010, etc. Okay, this is the basic configurations of digital signal transmission. Okay, resolution of digital output. Okay, resolution of digital output. Okay, remember well these formulations. Okay, delta. Okay, delta V out. Okay, digital output is equal to V reference. In this case, V reference times 2 to the power of minus n. Okay, to the power of minus n. N is what? The bit, number of bits. Say sometimes your data is 4 bit, sometimes 6 bit, sometimes 10, sometimes 11, etc. So this will be your values. Okay, the input voltage of ADC. Where is the input voltage of ADC? Okay, the input voltage of ADC is actually this part. Okay, is actually the output analog sensor signal after the operation amplifier. Okay, that is the input of ADC. This is the output of the ADC. The input of ADC is actually the output of analog sensor after it passed through the op amplifier. Okay, and number of bit and binary bit words. Okay, let's consider this work example. Okay, a measurement of temperature using a sensor that output, have a look here, 6.5 millivolt per degree Celsius. 6.5 millivolt per degree Celsius. So means that if 2 degrees Celsius, this one will give us a reading of 13. Correct? Must measure up to 100 degrees Celsius. Okay, it says here, a 6-bit ADC. It's mentioned here clearly, a 6-bit ADC with a 10-volt reference is used. Okay, so we use a 6-bit ADC and 10 volt. Okay, develop a circuit to interface the sensor and the ADC. Find the temperature resolutions. Okay, what we need to do now, first, okay, the sensor output. Okay, the sensor output at 100 degrees Celsius will be, okay, so 6.5 millivolt per degree Celsius. So for the maximum 100, we simply time 100. That will give us the maximum, okay, the maximum voltage to be 0.65. 0.65 volt. Okay, at 1 degree Celsius, it gives us 6.5 millivolt. Okay, so 100 times greater, we simply times and we will have 0.65 volt. Okay, the interface circuit must provide again, so that at 100 degrees Celsius, the ADC output is 11111. Okay, we know it is a 6-bit. Why it should be 1111? Because that is the maximum values. We know the 100 degrees Celsius is maximum, and the binary digit, you've learned the bit and digital in the digital electronic digit. 11111 is the maximum combination of all ones to be the maximum. So the input voltage of ADC that will provide this output is found from, okay, this is the V input of the amplifier. Okay, okay, V input of ADC. This is the value that we are going to search for, the input values. So what formula that we need to use? The V in ADC is equal to V out amplifier, which is this one. Okay, this one. Where is it? Okay, this one, V in. V in, V reference, binary 1, 2, 3, depend to up to 10. So we just use this one, 10. The reference is given and it's 6-bit. 1, 2, 3, 4, 5, 6. So 2 to the power of 1, to the power of 2, to the power of 3, 4, 5, and 6. So that will give us 9.84. Okay, that is the input values for the ADC. Okay, now you know this value 9.84. Okay, and you know the output value of this one of the current sensor is actually 0.65. Why 0.65? Because 100 degrees Celsius is equivalent to 0.65 output. Okay, now how we going to display 0.65 at this point. Okay, output for the sensor is 0.65, but the ADC are unable to read these values. Okay, so what it do is actually it use the amplifier to amplify to obtain a certain values here, so that is become readable. So how to calculate the amplifier gain? Amplifier gain is very simple. 9.8 maximum divided by the minimum. Then we know, I mean the input for the ADC divided by the output of amplifier. So we will should be able to calculate the amplifier. So the amplifier gain is 15.4. So actually, these are the circuit, okay? These are the configuration that you're going to establish. We have the sensor. The resolution of the sensor is 6.5 millivolt per degree Celsius. And then at the end, at 100 degrees Celsius, the output voltage will be 0.65. Why we consider maximum? Because we want to know the values of ADC, analog digital converter, at the maximum, so that we can calculate the output here, the input for the ADC, and then with this one we should be able to calculate the gain. So these are the circuit representation for us to convert analog to digital. Okay. Okay, next. Okay, for the second question, the temperature resolution can be found by working backward from the least significant bit. Okay, we just modify and rearrange the formula givens. So, okay, so V out, you know, V reference, V out and everything. V reference is 10. It is binary 2. Bit number is n. This is the formula as given here. Remember, digital signal transmission to convert the signal. Okay, so we will have 0.156 volt. And then working backward of the amplifier, we divide, and then that will give us a certain values, which is 0.01 volt. And then from there, we should be able to calculate the temperature sensor change. 1.3 divided by 0.065. So we will have for one voltage level will give a change of 1.59 resolution. Okay, temperature change. Okay, so have a look yourself, try to review. And then a measurement of liquid using ultrasonic has output of 6.5 millivolts centimeter. The circuit to be measured is 100 centimeter with 6 bit. It's mentioned here, 6 bit. If 6, you just use 6. How about if 4? If 4, we just use up to 4, which is in this value 1, 2, 3, 4. Only this 4. Okay. If 6, we just 6. If 8, we add some more, up to 8 values. Okay, develop circuit to interface. Okay, so the solution is there. It's exactly the same as I explained before. So we calculate what is the V in, reverse calculation, 6 bit, 64, and we should be able to calculate the V in here. So we need to know the voltage gain is 15.4. So, okay, in this case, have a look here. Okay, this is the general representation, and this is actually the circuit. We know the amplifier circuit is this one. So you draw, and you should know the values to calculate this one. So the gain will be 15.14. Okay, so you have a sensor, amplifier circuit, ADC. It's exactly in the previous work example. Okay, to conclude for this chapter, okay, guideline for analog signal conditioning design. Okay, first what we need to do? First, we need to define the measurement objective. Okay, we need to know what we're going to measure, what parameter to be used. Okay, what range. If it is water, boiling water, you know the range will be 0 up to 100 degrees Celsius. You're not going to, okay, we don't need to go up to 200, 300 because the maximum boiling temperature is just 100. So you can decide for that. The accuracy, you need to decide whether you can have a 5%, 3%, 10% tolerance, the measurement, and then next, after you decide the measurement objective, you need to select the right sensor. Okay, what is the right sensor? Okay, what parameter? What are the transfer function, response time, the range, and the power? You need to consider all those so that our instrumentation circuit and configuration are able to serve very well. Okay. Then, okay, design analog signal conditioning. Again, you need to know the parameter, range, input impedance, output impedance, the one that we calculate before. These are the things that we need to know. And then note on analog signal design. So we need to know all of this for us to able to design a good signal conditioning circuit. So that all signal from the input can be transferred to the output. I mean input of the control room, and the control room can communicate to the sensors, to other element, actuators, and any control element like a valve and etc. Okay. Have a look at this one, read by yourself. At least you need to know all of this guideline for the analog signal conditioning. And okay, transmission technologies. Okay, transmission technologies. Okay, these are something that you can have a look. Okay, for example, sensor to controller, signal representing the measured value sent to the controller. Okay, to control the measured value. And then these are the device that been available on market. We know that the sensor can be controlled by a controller. The sensors should be able to send the data to the controller, and nowadays we are moving towards IR 4.0. Everything is automation. You can control everything remotely. You have features, okay, calculation at the sensor, filtration, measurement, linearization, correction factor, etc. Okay, controller to the valve, and then this is a sensor to the controller. How controller can communicate to the valve? Okay, output controller IP ni, this one IP converter is current to pressure converter. Okay, to valve, because we need to convert, we need to see what is the valve pressure values, how to convert it into current, how to make it become useful data in our application. Okay, standard and etc. You can read by yourself. This is just readings. The advantage and disadvantage of the current technology. These are the traditional analog. These are the digital part of the recent technology. You can really see the difference in terms of the transmission. And for further info, you can actually read this website for additional knowledge. Okay. Okay, I think that's about it. For this week, for this section, for this chapter. I hope you more or less understand what I'm trying to say, and try to digest yourself, or maybe try to spend half an hour, 1 hour to read through the notes or to review what I just explained to you. And if you don't understand at any point, if you didn't get anything at any point, please raise to my concern in the next class next week. Okay. Mungkin maybe some of you now still figure out or still considering, maybe some of you not even listen to this lecture. You do add some other things, but it's entirely up to you. But what most important, you need to review, and I'm here to facilitate, just to further explain what are the highlight of the important note and points for this section. Okay. Okay, any questions so far? at this point? Iskandar, ada?
Tak ada doktor.
Faham tak Iskandar ke masih blur?
Ah,
Ke
so far so good.
so far so good? Okay. Hakim. Kau ni ngula je Hakim. Ada tak? Tengok dah tak ada dah. Tadi ye masuk gebor kan. Memang dah masuk gebor lah ni. Hakim ni. Okay, lagi Amir Amirul.
Ya doktor.
Okay, so far.
Faham.
Faham CK, okay.
Boleh doktor.
Boleh Sabrina.
Boleh doktor.
Okay, tak apalah. Saya tanya randomly je. Most of you kata boleh. Okay, I assume you faham lah. Kalau saya pun mungkin saya tak dapat lagi hari ni. You read once, you should be able to get to grasp what are the most important notes on this chapter. Okay. Okay, I think if you don't have any questions, I think it's better to stop now. And again, if you have any things, you can actually leave it for next week, and you can raise or ask me in the next class. And those who DM me for about attendance, etc., I take note on that. Even though sometimes I may not able to reply to you, I take notes on that and I'll try to address it. No problem about your attendance. Everything is okay. I'll just use and I'll try to convert it back to your class. No problem. And those who pass to me the evidence of the absence, please plus to me the supporting letter or evidence so that I can include in the attendance. Okay, anything just text me or WhatsApp me, or maybe if I didn't respond for a quick at your just remind me again. No problem. No hard feeling. No anything. You can remind me after 1 or 2 days, doctor. Any updates about this one, doctor? Just remind me. No issues. Sometimes there are too many messages, especially when I engage with the international office. There are too many messages coming. I've got 100 incoming email. WhatsApp daily basis. Sometimes I couldn't go through each of all these things. Provided you need to remind me. You need to remind me, alert me on anything. Thank you for those who always remind me. Thank you so much. And okay, that's about it for this week. Inshallah, I'll see you next week. We complete this class or finish this class with for Muslim bacaan tasbih kifarah dan suratul As. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Alright, thank you everyone. Have a good day. Stay safe. Hopefully you can pray for the best, everyone.
Thank you, doktor.
Thank you, doktor.
Okay, Assalamualaikum warahmatullahi
Thank you,
wabarakatuh.
Waalaikumsalam.
Thank you doktor.
Thank you everyone. Thank you.